Right now, there's this prehistoric bacteria that has basically been hunting humans since the days of ancient Egypt.
Mm.
And it's quietly sitting inside the lungs of like 1 out of every 4 people on Earth.
Yeah, it's a stunning reality check.
Yeah,
I mean, we tend to view modern medicine as this impenetrable shield, right? But the numbers coming out of these latest global health reports, they tell a very different story.
totally. And well, welcome to this custom-tailored deep dive. We're super thrilled to have you with us as we unpack this massive stack of sources you provided.
We've got official CDC guidelines, some incredible historical reviews, and cutting-edge 2024 medical papers on global disease burdens and diagnostic tech.
Right. So our mission today is to explore tuberculosis, TB, because for you listening, TB might sound like, I don't know, a relic.
Right, like a disease from Victorian novels where tragic characters faintly cough into silk handkerchiefs.
Exactly. But in 2022 alone, there were 10.6 million new cases of TB. It's actually the second largest infectious disease killer globally, sitting right behind COVID-19.
Which is just a profound tragedy when you consider the fundamental biology of the pathogen. I mean, this an entirely preventable and curable disease.
Yeah.
Yet it continues to outmaneuver our global health infrastructure year after year.
So we're going to trace this pathogen from its ancient origins, break down the exact biological mechanics of how it spreads, and look at the futuristic tools from like AI algorithms to things called electronic noses being deployed to finally eradicate it.
Yeah, the tech side is mind-blowing.
It really is. Okay, let's unpack this because to really grasp the modern fight against TB, we have to understand the timeline. If you imagine humanity's history as a house, TB is, it's basically an incredibly resilient, unwelcome squatter that has been hiding in our basement since the very dawn of our species.
That's a great way to put it. And what's fascinating here is the evolutionary timeline. It's just staggering. The genus Mycobacterium, which tuberculosis belongs to, actually originated over 150 million years ago.
Wait, 150 million, so like the Jurassic period.
Exactly. The ancestors of this bacteria were evolving alongside dinosaurs. And by the time early hominids were walking around East Africa roughly 3 million years ago, an early progenitor of the TB we know today was already infecting them.
That is wild. And it wasn't just ancient hominids either. Like, we usually associate Pott's lesions with 19th century medical textbooks, right?
Right, yeah.
But our sources note that archaeologists have actually found evidence of these lesions in Egyptian mummies dating back to 2400 BC.
Yeah, finding structural bone collapse caused by TB in ancient pharaohs, it completely reframes how long this pathogen has been successfully colonizing the human body.
Just living in there, eating the bone.
Yeah, and it highlights a crucial misconception. Because TB is transmitted through the air, we categorize it strictly as a respiratory disease.
Like a lung thing.
Exactly.
Yeah.
But once the Mycobacterium tuberculosis enters the lungs, it can breach the pulmonary system, enter the bloodstream, and just travel anywhere. When it anchors in the spine, it begins to slowly consume the vertebrae. That structural decay is what we call Pott's disease. The fact that we see this in ancient Egypt proves the bacteria had already, perfected its survival mechanisms millennia ago.
Man. And then, so we jump forward to the Middle Ages, and the disease manifests in this entirely different, highly visible way called scrofula.
Yes, the king's evil.
Right. The history books called it the king's evil. Patients weren't just coughing, they were developing these massive, purulent, swollen masses on their necks.
It's brutal. That happens when the bacteria targets the cervical lymph nodes. And the societal response to scrofula is just a fascinating study in human desperation.
Because they had no idea what was actually causing it.
Exactly. Because medieval society lacked any understanding of microbiology or germ theory, they turned to divine right. There was this widespread, genuine belief that the physical touch of a French or English monarch could magically cure it.
Like a king or queen chosen by God touching your neck would heal you.
Right. It's the ultimate placebo effect born out of total medical darkness.
Yeah. But then the disease profile shifts radically during the industrial era. It stops being this mysterious affliction of kings and mummies and explodes into a widespread urban epidemic. They started calling it the White Plague or the robber of youth.
Well, the Industrial Revolution created the ultimate vector for an airborne pathogen, which is rapid, unchecked urbanization. You suddenly have thousands of people migrating from rural areas into these cramped, poorly ventilated, damp factory slums.
Just a perfect breeding ground.
Exactly. The bacteria thrived in those conditions. It decimated young, working-class populations. And it earned the White Plague moniker because the disease slowly consumes the body's resources, leaving the patient with a severe anemic pallor.
Man. And our historical source notes that in 1720, an English physician named Benjamin Martin guessed it might be infectious. But the real turning point wasn't until 1882, right?
Yeah, 1882. That's when the German scientist Robert Koch finally isolated the tubercle bacillus.
Right. He proved it wasn't a genetic curse or caused by bad air, but it was a living microorganism, which brings up a really critical question about the present day. If we've known exactly what this organism is for over 140 years, how is it still infecting 10.6 million people a year?
That is the million-dollar question.
So let's break down the mechanics of transmission. How does this thing actually spread?
So the mechanism is purely airborne, but it requires a very specific delivery system. When a person with active TB in their lungs coughs, speaks, or even sings, they expel these tiny infectious particles called droplet nuclei.
Okay.
And these are microscopic, like much smaller than typical respiratory droplets.
And our CDC source is incredibly explicit about what TB is not.
Yeah.
Because you cannot catch it by shaking hands, sharing food, touching a contaminated surface, or kissing.
Right. It is strictly respiratory. You have to inhale those microscopic droplet nuclei.
And because they are so small, they bypass the natural defense mechanisms of your upper respiratory tract.
Right. Exactly. They slip past the mucus and the sweeping hair-like cilia in your throat, and they travel deep into the furthest, most vulnerable reaches of the lungs, the alveoli.
But inhaling the bacteria doesn't guarantee you get sick, which is wild.
No, it doesn't. This is where the biological chess match begins.
Let's talk about that chess match, because the numbers here are mind-blowing. Our sources say an estimated 26% of the global population has latent TB.
Yeah, over a quarter of humanity.
Over a quarter of humanity. The germs are in their bodies, but the people aren't sick, they have no symptoms, and they are completely non-contagious. If 26% of the world is walking around with this pathogen, why aren't we all constantly sick?
It comes down to cellular imprisonment. When the bacteria reaches the deep lung tissue, your immune system recognizes the invader and dispatches white blood cells called macrophages to swallow it.
Like little Pac-Man.
Basically, yeah. But TB is incredibly tough. It can actually survive inside the macrophage. So your immune system pivots. It sends a swarm of cells to build a physical, calcified wall around the infected area.
Okay, wow.
This structure is called a granuloma.
So it's like a microscopic prison cell built out of your own immune system.
A perfect analogy. As long as your immune system is robust, the prison guard stays strong, the wall holds, and the TB remains dormant or latent.
Okay, but what happens if the walls break?
Well, if the host's immune system weakens due to aging, severe stress, malnutrition, or another illness, the granuloma wall begins to crumble. The bacteria break out, multiply rapidly, and latent TB transitions into active TB.
And without medical intervention, active TB is fatal.
Yes, it is.
So statistically, if you listening or riding on a crowded subway train right now, several people around you have this bacteria walled off in their lungs, completely unaware of it.
Definitely.
So who is losing that immune system battle today? Looking at the 2021 and 2022 demographic data in our sources, the global burden is heavily skewed toward men, specifically in the 15 to 69 age group. What is driving that massive disparity?
The data points clearly to occupational and behavioral risk factors that actively compromise the immune system or the lung tissue itself. Like, men are statistically overrepresented in high-risk environments like mining and construction.
Ah, right.
Constant inhalation of silica causes microscopic scarring in the lungs, making it much harder for the body to maintain those granuloma walls. But the absolute primary driver for men is tobacco use.
Because smoking doesn't just damage the tissue, it paralyzes the cilia we talked about earlier, and it suppresses the localized immune response in the lungs.
Yeah, you are essentially starving the prison guards of oxygen.
Wow. And what about women?
Well, the data shows a different primary risk factor for women, which is high fasting plasma glucose. That's the clinical marker for diabetes.
Okay, so how does diabetes affect the lung prison?
Diabetes causes chronic systemic inflammation and fundamentally impairs the function of those macrophage cells. High blood sugar makes the immune cells sluggish, giving the dormant bacteria the perfect biological window to escape.
Which maps perfectly onto the global socioeconomic data in the papers. They use something called the Socio-Demographic Index, or SDI, which measures a region's income, education, and fertility rates. And unsurprisingly, there is a massive negative correlation between SDI and TB burden.
If we connect this to the bigger picture, the lower the socioeconomic status of a region, the higher the TB rates. Poverty creates the ultimate catalyst for the disease.
Right.
If latent TB becomes active TB when the immune system drops, then systemic malnutrition, overcrowded living conditions, and a lack of access to basic preventative health care are the exact ingredients required to trigger an epidemic.
So if a quarter of the world has this wall built around the bacteria, the real medical mystery isn't just treating the active cases. It's figuring out who has a crumbling wall before it fully collapses and they start infecting others.
Exactly.
How do you find a microscopic pathogen that is actively trying to hide?
Historically, our methods have been painfully inadequate. The most common diagnostic tool used globally is still sputum smear microscopy, which is a technique invented over a century ago.
Which is basically looking at phlegm under a microscope.
Pretty much. A technician takes a sample of a patient's phlegm, stains it with a specialized dye, and looks through a microscope to manually count the bacteria.
Aside from being incredibly tedious, it has a massive flaw, right? It relies entirely on bacterial load.
Yes. If a patient is in the early stages of active TB and there aren't millions of bacteria in the sample yet, the technician simply won't see them.
So you get a false negative, and you send a highly contagious person back into their community.
Exactly. And while culturing the bacteria in a lab is highly accurate, TB grows at a glacial pace. Waiting weeks for a culture result is useless in an outbreak scenario.
What about x-rays? Don't we use those?
We rely heavily on chest x-rays, sure, but traditional x-rays lack specificity. They show an abnormality like a shadow or a scar, but they can't definitively tell a doctor whether that shadow is active TB, a previous bout of pneumonia, or just general lung damage.
Right, so you are looking at a really murky diagnostic landscape.
Very murky.
But the 2024 sources detail a massive revolution in diagnostic tech. Science is finally building the tools to see through that murk, starting with molecular tests. Specifically these NETs, like the GeneXpert system.
Yeah, NET stands for Nucleic Acid Amplification Test. Instead of relying on human eyes to spot a died bacterium, these machines look for the unique DNA signature of the Mycobacterium.
Oh, smart.
Even if there is only a tiny trace of the bacteria in the sample, the test chemically amplifies the genetic material until it is detectable.
And it goes deeper than just detection, right? The machine can actually read the genetic code of the bacteria to see if that specific strain possesses a mutation that makes it resistant to rifampicin.
Right, which is a frontline TB drug. Knowing instantly whether standard medication will work or fail saves critical weeks in a patient's treatment timeline.
It fundamentally changes the speed of clinical decision-making.
Oh, absolutely. But we're also seeing artificial intelligence modernize our older tools. Deep learning algorithms are now being deployed to read chest x-rays.
Yeah, the papers describe how developers trained these AI models on millions of lung scans. You feed a digital X-ray into the system, and the AI can detect incredibly subtle parenchymal lesions.
Right, huge.
Yeah, and to clarify for you listening, parenchymal tissue is the functional part of the lung where gas exchange happens. The AI can spot microscopic inflammation or tissue damage in those specific areas that a human radiologist might easily miss just due to fatigue or the sheer volume of scans.
Right. And by acting as a highly sensitive automated filter, the AI significantly reduces the diagnostic bottleneck. Clinics use the AI to scan everyone quickly and cheaply.
And then they only test the flagged ones.
Not exactly. They only run the expensive, time-consuming molecular lab tests on the specific patients the AI has flagged as high probability. The sources indicate this can reduce the need for laboratory tests by 50%.
That's incredible. And we're also seeing innovations in how we test the body's reaction. There's a new fingerstick blood test mentioned called the Cepheid MTB host response.
Yeah, this one is fascinating.
Instead of looking for the bacteria itself, it measures a 3-gene mRNA score in the blood. Basically, it's reading the specific molecular alarm bells going off inside the host's immune system.
It is a brilliant pivot in diagnostic strategy. If the bacteria is hiding, don't look for the bacteria. Look for the specific biochemical panic it causes in the host's white blood cells.
Okay, but here's where it gets really interesting. The absolute wildest piece of technology in our stack of sources is the electronic nose.
Oh yeah, this is straight out sci-fi.
Right. There is a device currently undergoing clinical trials in Cameroon that literally smells tuberculosis.
The underlying science is deeply elegant, actually. When the TB bacteria metabolize and multiply inside your lungs, they produce waste. They release specific volatile organic compounds, or VOCs.
Think of them as tiny airborne chemical burps.
Exactly. And when you exhale, the air coming from the deepest part of your lungs, the alveolar breath, carries those specific chemical signatures out of your body.
So how does the nose actually smell it?
Well, the electronic nose uses a sensor array modified with metalloporphyrins.
Say that again?
Metalloporphyrins. You can visualize them as highly specialized chemical magnets that are tuned to attract and bind to the exact gases produced by the TB bacteria.
Wow.
When a patient breathes into the device, it analyzes the chemical composition of their breath in real time. In clinical settings, it achieved an 88% accuracy rate at diagnosing active pulmonary TB.
It's literally a high-tech breathalyzer for an ancient plague. But I have to push back here.
Sure.
Because you're talking about deploying highly sensitive AI algorithms, molecular DNA amplifiers, and chemical sniffing electronic noses. But earlier, we established that the socioeconomic reality of TB means it hits hardest in the poorest, most rural parts of the globe.
Right.
So is setting up an AI-equipped diagnostic center in a remote village that barely has reliable electricity a feasible solution? Or is this just, utopian tech bro optimism?
Well, that is the exact friction point global health organizations are wrestling with right now.
Sure.
High-tech wizardry is useless if it requires an air-conditioned laboratory and a team of software engineers to calibrate it. The ultimate goal highlighted in our sources isn't just advanced tech. It is developing point-of-care triage tests.
Meaning diagnostic tools that are cheap, rapid, and require zero electricity or specialized training.
Exactly. Something as simple and durable as a lateral flow pregnancy test or a rapid COVID test. The technology must adapt to the environment, not the other way around.
Which leads us to the strategic roadmap. If we understand the biology of the spread and we are refining the diagnostic tools, how do we actually stop the pathogen permanently?
The sources outline a major philosophical shift in prevention. For decades, the global strategy was reactive. Wait for a person to get sick, then treat them.
But the new mandate is proactive. We have to go after the squatter while it is still trapped in the granuloma prison.
Yes. We need to actively treat latent TB in vulnerable populations.
So if a patient is diagnosed with HIV or presents with severe, uncontrolled diabetes, we know their immune system is compromised.
Right, and the strategy now is to immediately administer a course of preventative anti-TB medication to kill the dormant bacteria before the host's immune walls ever have a chance to collapse.
The same proactive philosophy applies to how we locate the disease, too. The old model was passive case finding. You wait for a patient to feel so incredibly sick that they finally walk miles to a hospital and ask for help.
But by the time they do that, they have been coughing in their community, on public transport, and in their homes for months.
Exactly. So the modern approach is active case finding.
Yeah, we use mobile units now. Vans equipped with portable digital X-ray machines and AI software running on laptops. And we drive them directly into high-risk, crowded environments. We actively screen prisons, homeless shelters, refugee camps, and isolated rural communities.
And for you listening, you might wonder why international resources should be poured into funding mobile X-ray vans in remote villages thousands of miles away.
That's a fair question.
But beyond the obvious humanitarian imperative, the biological reality is that airborne diseases do not respect geopolitical borders. Furthermore, if we leave TB unchecked, it doesn't just spread, it mutates into something far worse.
That is the nightmare scenario keeping epidemiologists awake at night. The standard treatment for TB takes months of strict medication adherence.
And when patients start feeling better after a few weeks, or when they simply run out of money or physical access to the clinic, they stop taking the drugs.
Which is the worst thing you can do. When you stop an antibiotic regimen early, you only kill the weakest bacteria. You leave the strongest, most resilient mutants alive in the lungs.
So they multiply.
Yes, they multiply, and the patient develops multi-drug-resistant TB or MDR-TB. The standard frontline drugs become completely useless. The treatment for MDR-TB takes years, the side effects are absolutely brutal, and the mortality rate skyrockets.
This raises an important question about funding, which the WHO's target to eliminate the global TB epidemic by 2030 hinges on.
Right. The Lancet Commission report, in our sources, makes it very clear that international grants are no longer sufficient. To achieve the 2030 goal, international funding must be strategically tied to middle-income countries mobilizing their own domestic resources.
It requires a sustained, shared economic commitment.
It really does. It also requires community-level intervention through a concept called task shifting.
Task shifting. What does that look like on the ground?
Well, we cannot rely solely on a limited pool of highly trained physicians. We have to train local community health workers to administer tests, provide comprehensive health education to families, and physically monitor patients to ensure they finish every single pill in their months-long regimen.
So you destroy the stigma and stop the chain of transmission right at the household level.
Exactly. We are fighting an organism that has had 150 million years to perfect its survival. Defeating it requires combining the most advanced molecular science with the most fundamental human diligence.
What a phenomenal journey this source material has taken us on. I mean, we've traced a pathogen from its prehistoric origins, eating away at the spines of Egyptian pharaohs, through the desperate eras of royal touches and industrial plagues, all the way to the modern socioeconomic battleground.
And we are finally armed with the biological understanding and the technological tools, from amplifying invisible DNA to algorithmic lung scans, to rip down the walls this bacteria hides behind.
It's truly amazing. Well, I want to leave you with one final provocative thought to chew on today.
Okay.
We discussed how an electronic nose can already smell the unique chemical burps of tuberculosis on a person's breath with 88% accuracy. If the fundamental technology to analyze breath chemistry is already working in clinics today, how long will it be until our smartphones or our smartwatches are equipped with microsensors that can diagnose hidden, ancient diseases just by having us exhale onto the screen?
Wow. That is a truly wild prospect to consider. The future of personal diagnostics is coming fast.
It really is. Thank you for joining us for this deep dive. Stay curious, keep asking questions, and we'll see you next time.